In this recording, we will discuss startup of a mixed flow reactor. Mixed flow reactor. So we added the missing term here. The balance equation that we have learned already is on the board. It is the time rate of change of total number of moles of species A within the system boundaries. That is equal to the net rate that component A enters through the system boundaries minus the net rate with which the component A leaves through the system boundaries. And this term represents the consumption of component A within the system boundaries at a rate indicated by RA. V is the volume of our reactor. Now I'm going to define, remind you, the two new terms. One is the volumetric flow rate of the components that is coming in and out of the reactor, and rho represents the density of the fluid. They are both going to be treated as constants. They are not going to change. The reason that I bring this up is that I'm going to write an overall material balance, total material balance. The time rate of change of total mass within the system boundaries is going to be equal to the net rate that mass flows into the reactor minus the net rate that mass flows out of the reactor. I'm going to represent those masses in terms of volumes, volumetric flow rates, and densities. M is the total volume times the density of the fluid, and M dot is the volumetric flow rate times the density of the fluid. And we have identified the densities and the volumetric flow rates as constants. We haven't said anything as such for the total volume. Now let's write our balance equations with constant density assumptions. Density is constant. As a result, I'm going to take the out of the derivative, and my dm becomes dv over dt, and that is going to be equal to v0, we also taken this as constant, times rho that enters through the system boundaries minus v0 times rho that leaves the system boundaries. Now rho was constant, and I'm going to cancel them out from the equation, and I get dv over dt to be equal to v0 minus v0. This is going to be 0, and the solution of this differential equation will tell me that my total volume is not changing. So the derivation's purpose was to give you a hint about the underlying principles of constant density and constant volumetric flow rate. So when we say constant density and constant volumetric flow rate, that leaves the volume of our reactor constant. Now with this, I'm going to go back and I will rearrange the overall species mole balance, dNA over dt being equal to FA in minus FA out plus RA times V. And I'm going to solve this equation for you for the startup of a mixed flow reactor. Remember, our volume is constant. As a result, NA being defined as CA, and I'm going to drop out from the definition, I'll just label the concentration as CA times volume. And as a result, dNA over dt will be V. I have taken V out of the different derivative because it is constant, d Ca over dt. The other side of the expression is Fa in, remember V0 is constant, V0 times Ca in minus V0 times Ca out. Remember, I dropped out from the definition, from the identifier, minus plus Ra times V. Right? So I'm going to divide both sides of this equation by V0. To obtain tau. Remember, tau was V over V0. It was the space-time. dCA over dt, that is equal to Ca in concentration of the stream that enters through the system boundaries minus Ca plus R sub A. And we are solving these equations for a hypothetical A goes to products type of a reaction. And we define its kinetics as minus R sub A is equal to K times Ca, following from the previous recordings. So I will substitute K times Ca minus K times Ca for the R sub A and my final differential equation. And I have, of course, a tau here. All right? And my final expression will be tau dCA over dt, that is equal to Ca in minus Ca plus minus tau K Ca. And I will rearrange and solve this equation in the other frame. So now let's divide our board for the problem definition on one side and problem solution on the other side. So here on this frame, I will carry out the mathematics to obtain an expression, and then I will discuss the final equation in terms of its physical significance. First, I will carry my differential equation here, dCA over dt, tau dCA over dt. This is equal to Ca in minus, now let me group the terms that have Ca. Ca 1 plus tau k. Remember, tau k was the Damköhler number. It was a dimensionless quantity. And now I need a boundary condition. My boundary condition will represent a stirred mixed flow reactor, which is initially filled with pure solvent. All right. At time t is equal to 0, Ca is going to be 0 because I have only solvent in this reactor. But I have a liquid. The tank is filled with the solvent. At time t is equal to 0, I start introducing my solute, my reactant, into the feed stream, and I monitor I monitor the product stream. Okay? My product stream is at the same concentration as the contents of the reactor. This is the condition of a well-mixed reactor, well-mixed flow reactor. Yes, now this is my boundary condition or initial condition at time t is equal to 0, Ca is equal to 0. So this is where I'm going to generate my solution. Well, this is going to need some rearrangement. I will collect Ca containing terms on one side of the expression and time containing terms on the other side of the expression. I have dCa over Can minus Ca times 1 plus tau k on this side, and I'm going to have 1 over tau dt on the other side. When I integrate both sides, I need to add an integration constant I will call phi. All right? This integral is fairly straightforward. Here I will need to make a change of variable. I will define a new variable. My new variable is going to be called u, which is equal to Can. And remember, Can is a constant, minus Ca times 1 plus tau k. And as a result, if I take the derivative of u, this should be 1 plus tau k with a minus in front, dCa. So I'm going to take dCa from here in terms of du and substitute here to obtain integral du with a minus in front. Let me put the minus here. And let me take those constants outside the integral. 1 over 1 plus tau k divided by u. See, my integral has simplified. Let me carry out the integration on the other side. It is t over tau plus phi, the integration constant. This is ln u, and I will substitute u back into the equation. I will carry out this algebra as 1 over 1 plus tau k times ln of u, and u is this, Can minus Ca 1 plus tau k. Which is equal to t over tau plus phi. Now I'm going to substitute my initial condition at time t is equal to 0, Ca is equal to 0. So when time t is equal to 0, this term is equal to 0. My integration constant, Ca is equal to 0. This term disappears. I am left with minus 1 over 1 plus tau k times ln Can. That is my phi. Right? So I substitute this for phi, and I have an expression for t. T is equal to tau. I carried this to the other side of the equation. Times this was on this side of the equation. When it is carried to the other side, it lost this minus sign. So I'm going to have them in the same common denominator, 1 plus tau k times ln Ca in minus, it is this minus, ln, let me make this fancy bracket so that I will have my square bracket here, Ca in minus Ca 1 plus tau k, all the brackets, and I will do one more step of rearrangement. I will write them as ln, this divided by that, and I will just do a trick of having a negative term, and I will explain why I need to have a negative term in a moment, minus tau divided by 1 plus tau k times ln Ca in divided by Ca in 1 minus Ca divided by Ca in. Let's keep our fancy and square brackets. Times 1 plus tau k, our square bracket and our fancy bracket. Actually, we don't need those brackets now. ln takes care of this. Okay? So this is our expression. Now we have an equation that allows us calculate how much time it takes in order to have a concentration of Ca, if our Ca in is this, if our space-time is that, if our rate constant is that. So this is the expression that relates time to the concentration. But sometimes we are more interested in how much time it takes for our concentrations to achieve a certain value. So I'm going to discuss the merits of this equation and of this curve. Now let's first do the limiting analysis to check if our derivation is correct. What is going to be the limiting analysis? As time goes to infinity, the solution should converge to the steady state solution. And this is how I discovered that I was missing one term in this equation. The term, as time goes to infinity, is going to be a negative exponential, and this negative is going to diminish this term from our equation. And for the asymptotical solution, our concentration approaches to the inlet concentration divided by 1 plus tau k. Remember that that was the steady state solution for our first order reaction taking place in a mixed flow reactor. So as time goes to infinity, concentration of A should go to the steady state solution. This is how you're going to check if you are making a mistake or not in your derivations. Now let's come back to the universality of this curve. The curve is qualitatively universal, but quantitatively it is going to be different for each tau, for each k, for each Ca in. Now if we normalize these terms and have dimensionless quantities, and this is the merit of dimensionless quantities, that its predictions are going to be universal. First, I'm going to make the concentration non-dimensional by dividing it by Ca in inlet concentration, which is a constant. And I'm going to non-dimensionalize the time by dividing it by the space-time. So I have two non-dimensional quantities. Okay, one of them is a non-dimensional concentration. I will call that Ca bar. That is going to be Ca divided by Ca in. All right, and the other one is T bar. It is going to be T over tau. Okay, so I non-dimensionalized the dependent and independent variables with respect to our reactor conditions. Now, this behavior that I'm going to redraw on a smaller diagram, behavior will be identical, but prediction will be universal. Okay? So, here the system converges to the steady state concentration given that the reactor has this space-time. The exercises that you will have, in addition to generating as many curves as possible, are going to be to show that you need 5 tau equivalents of time to reach 95% of the steady state concentration. Okay? You need 5 tau equivalent in order to reach 95% of the steady state concentration. In this recording, we will go over the batch reactor analysis starting from the general balance equation. Our general balance equation is reflected. It is dNA over dt, which is equal to Fa in minus Fa out plus Ra times V. Again, we are working, we are generating our solutions for a generic hypothetical first order reaction of A going to products, and it is reaction rate is given by minus Ra is equal to K times C sub A. Now the batch reactor is a perfectly mixed, for our analysis in this problem is concerned, it's a perfectly mixed, it's a well mixed reactor, but there is no feed, there is no outlet. And as a result, our general balance equation loses these two terms. This becomes 0 for the batch reactor, there is no inlet. This becomes 0 for a batch reactor, there is no outlet. So we charge our reactants and we let the system evolve to the final product, and we take out our products. And given that, our balance equation simplifies dNA over dt to be equal to Ra times V. And again, this reactor has a constant volume process because of the time evolution of the reaction. Density doesn't change. Remember that there are certain reactions that densities can dramatically change, such as polyurethane synthesis, but this is not such kind of a reaction. The density doesn't change, volume doesn't change. And since volume doesn't change, our definition of Na, which is equal to V times Ca, simplifies to V times dNA over dt to be equal to Ra times V. V's cancel. I'm sorry, Ca. This is supposed to be Ca, dCa over dt. Okay, and we substitute Ra dCa over dt. We substitute for R sub A, which is a minus K times Ca, and integration, as we have done for a more complex system in the previous video. With an integration constant phi and with an initial condition at time t is equal to 0, Ca is equal to, this time Ca 0, 0 time concentration. All right? And this integration yields ln of Ca, ln of Ca, that is equal to minus K times T plus integration constant. At time t is equal to 0, Ca is equal to Ca0. This phi becomes ln Ca0. So on this side it is positive. If it is going to come here, it is going to be negative. We will do the ln algebra, so it will be ln Ca over Ca0 to be equal to minus K times T, or Ca is equal to Ca0 e to the minus K times T. There's a time evolution of Ca. There's a time evolution of Ca. This is the design equation for a batch reactor. The cleaned up version is here. dCa over dt is equal to R sub A and this is its solution for a first order reaction. In this recording, we will continue our conceptual development of the different types of reactors and their behavior. And here we will derive the design equation for a plug flow reactor, as we learned so far, is a tubular reactor where the fluid element is moving like a plug. In other words, it's not mixing with the fluid element in front of it, nor it is mixing with the fluid element behind it. So here I'm going to define a volume element which is going to start at Z, and it is going to end at Z plus delta Z. And this is going to be a cylindrical geometry. The cross-sectional area of this system is going to be A sub C. All right, so my differential volume element is delta V, that is equal to delta Z multiplied by A sub C. I'm going to write my balance equation under steady state conditions around that differential volume element, not around a macroscopic system boundary, but a microscopic differential volume element. So, again, because it is steady state, at steady state, right? What is steady state? Time evolution under force flows is 0. At steady state, dN over dt term is 0. There is no time evolution term. That I have fluid molar fluxes Fa. This time I'm writing this balance equation across this differential volume element. The entering Fa is Fa at Z. The outgoing molar flux is Fa at Z plus delta Z. The same term plus Ra times V. They're all equal to 0. I would like to draw your attention to the analogy between this expression and this general expression. We lost this term because our system is operating at steady state. Now this volume element, of course this is the differential volume element, right? It's not the total volume, but it is the differential volume element. I'm going to substitute this definition in here, okay? And I will do some rearranging. First, I will take these to the other side of the equation. Fa at Z plus delta Z minus Fa at Z. This is the other side of the equation. They change sign. Is equal to Ra times delta V. Delta V is equal to delta Z times A sub C. I will divide both sides of this equation by 1 over delta Z times A sub C, or delta V. And I will take the limit as delta Z goes to 0. Okay? And as a result of this mathematical intermediate steps that you should be able to do with relative ease, what I get is dFA over dZ 1 over A sub C to be equal to R sub A. Or I can combine those two terms and write this as a dFA over dV as R sub A. Okay, this is the design equation for a plug flow reactor. I will carry the analysis one step further. Here, let me generate myself a new clean frame. I will redefine FA in terms of its constituents. Remember, FA was CA times volumetric flow rate. So, if volumetric flow rate is constant, then my DFA can be defined as V times dCA, and the design equation takes the following form: dCA over d tau to be equal to R sub A. For a constant volumetric flow rate system. So I want you to compare this expression, dCA over d tau to be equal to R sub A, with this expression, dCA over dt is equal to R sub A. This was the design equation. This was the design equation for a batch reactor. This is the design equation for a plug flow reactor where volumetric flow rate is constant. This was the design equation for a batch reactor for constant volume. And the mathematical similarity should be kept in mind. Here, the parameter time is the astronomical time, the time that you observe with your clock, with your watch. This is the space-time, the time it takes this fluid element to traverse from here to here. All right? But they both have the units of time. This is the same constitutive relationship, R sub A, as we defined already as K times CA. And this is the same CA, the same CA.